Welcome to this explainer. Okay, today we are tackling something that, at first glance, probably just looks like a basic test prep tool, the AP Grid Robot. But seriously, do not let its deceptive simplicity fool you, because when you strip away the physical hardware, this little robot on a grid actually acts as a gateway to understanding some of the absolute deepest, most fundamental theories in all of computer science. So, grab a mental notepad. We're going to trace exactly how a simple mechanical agent bouncing around a screen connects directly to the very foundation of computing.
Here is the roadmap for our journey today. First, we'll meet the grid robot. Second, Turing's grand idea. Third, the robot command set. Fourth, tracing a straight path. Fifth, navigating around obstacles. And finally, number 6, the ultimate bug hunt. Okay, let's dive into this.
Section 1. Meet the grid robot. Deceptive simplicity.
How we define this robot is actually fascinating. It is an abstract computational agent. Think about it. If you take away the physical hardware, like you just completely forget about the motors, the sensors, the metal chassis, what you're left with is a pure finite state machine. The robot occupies exactly one cell on a rectangular grid at any given moment, and it faces one of 4 cardinal directions. That's it. Its entire state is simply its coordinate position plus the direction it's facing. Every single command it executes is just transitioning it into a new state.
Section 2. Turing's grand idea, the foundation of computing.
That pioneer of the state machine is Alan Turing. Born in London in 1912, he graduated from Cambridge in 1934, and just 2 years later, he published his foundational paper on computable numbers. And that paper established the theoretical basis of computer science decades before anyone ever built a physical computer. He also famously led the team that broke the Enigma cipher during World War II and later proposed the Turing test in 1950. Tragically, Turing was prosecuted in 1952 for his sexuality under British law and died in 1954. He was, however, posthumously granted a royal pardon in 2013.
In that 1936 paper, Turing imagined a hypothetical machine with an infinite tape, a read-write head, and a finite set of transition rules. Now, any mechanical procedure can be described as state transitions on a tape. Sound familiar? Because the crucial takeaway here is this. The grid robot model we're studying today is a direct descendant of Turing's grand idea. The robot is the agent, its commands are the transition rules, and the grid is the tape. This equivalence between abstract state transitions and physical computation is literally the reason why every programming language, every algorithm, and every microprocessor ultimately boils down to these exact same mechanics.
Section 3. The robot command set. Rules of the game.
So our robot lives on its rectangular grid and faces north, south, east, or west, and it understands exactly 4 commands. It can move forward 1 cell, it can rotate left or rotate right, which changes its compass facing but keeps its position exactly the same, and it can check its environment using can move in a specific direction. Those 4 simple commands are all we need to combine iteration, selection, and spatial reasoning into some truly brilliant algorithms. But before we start building those algorithms, I've got a massive warning for you straight from the source material. When you're evaluating these problems, missing a rotation is the absolute most common error. You have to always track both the position coordinates and the facing direction. If your robot is at, say, column 2, row 2, and you somehow forget that it's facing north instead of east, your next move forward is going to send the whole algorithm completely off course.
Section 4. Tracing a straight path, building complexity.
Let's kick things off with a pretty straightforward example. Step 1. Our robot's initial state is at column 1, row 1, and it's facing east, which is to the right. Step 2. We hit a loop that tells the robot to repeat 4 times. Step 3. Inside that loop, we just have a single action, execute move forward.
I want you to take a brief mental pause here. Can you predict the final position? Okay, so we start at 1-1 facing east. After move 1, we update the state to 2-1. Move 2 takes us to 3-1. Move 3 goes to 4-1, and our final move 4 lands us perfectly on the goal cell at 5-1, still facing east. Applying commands sequentially and recording that new state is exactly how you trace a loop.
Section 5. Navigating around obstacles, using can move and selection.
All right, let's raise the stakes with a new setup. The robot starts again at 1-1 facing east. Our target goal is located at 5-3, but this time we've got a solid obstacle blocking the path right at cell 3-1.
Let's see how this translates into our code. We have a loop repeating 4 times. Inside the loop, the robot has to make a choice. If it can move forward, it simply executes a move forward command. But else, meaning its path is blocked, it has to execute a specific sequence of 4 commands to bypass the block. Rotate left, move forward, rotate right, and move forward.
So let's trace these iterations carefully. Iteration 1, starting at 1-1, facing east. Can it move? Yes, the path to 2-1 is clear, so it moves. Iteration 2, now it's at 2-1, facing east. Can it move? No, that obstacle is right in front of it at 3-1. So the else block triggers. It rotates left to face north, moves forward to 2-2, rotates right to face east again, and then moves forward to 3-2. Now for iteration 3, the path ahead is clear, so it just moves to 4-2. And in iteration 4, clear again, moving to 5-2.
Okay, so the loop is completely finished. But the real question is, did the robot actually reach the goal? Let's compare. Our final computed robot position is 5-2. But our designated goal position was 5-3. And this brilliantly illustrates a core concept in computer science. An algorithm can execute perfectly without crashing. It can successfully navigate around an obstacle and yet still be functionally incomplete because it just fails to achieve the desired outcome. The robot safely bypassed the block, but it completely missed the target. Section 6. The Ultimate Bug Hunt Error Trace Workshop. Check out the setup for this complex environment. The robot starts at 1-1, but notice it is facing north this time. The goal is far away at 5-5, and we have this solid wall of obstacles blocking cells 3-1, 3-2, and 3-3. And here's the provided algorithm sequence. Move forward twice, rotate right, then a loop repeating 4 times to move forward, then rotate left, then move forward 3 times. I challenge you to trace this mentally. Track the state, the coordinates, and the direction, step by step. Because, spoiler alert, the algorithm is flawed. It will not safely reach 5-5. Predicting exactly which cell it visits when it veers off course or crashes is the true test of your tracing abilities. Before we wrap up, let's look at one final rapid-fire practice scenario directly from the source text. A robot starts at 1-1, facing east. Assuming no obstacles, it executes rotate left, move forward, rotate right, and move forward. Let's trace it out. Rotating left makes it point north. Moving forward takes it up to 1-2. Rotating right makes it point east again. And moving forward one last time lands it precisely at 2-2, facing east. I'll conclude our explainer with one last provocative question to get you thinking about the absolute limits of this environment. What exactly does can move forward return when the robot is sitting at the very edge of the grid, facing outward toward the boundary? Think about what it means to be a bounded state machine and how boundaries behave just like obstacles. Keep practicing those state transitions, trace carefully, and always remember the golden rule of algorithm tracing.